the base of the solid. S is a region enclosed by the graph of y equals the square root of ln of x. Let's take a look at that. The line x equals e, so we'll keep that in mind. And cross sections of S perpendicular to the x-axis are semicircles. Okay, so you have an idea in mind for that. So let's take a look at the picture. I'm going to just draw a quick perspective drawing. Draw a perspective drawing, that's fun. So something like this. So x equals e. So what I'll do is evaluate this function, second trace option 1, type in the e, so second division brings up the e, and that gives me a coordinate where I can expect to find e. So this is x equals e. And this coordinate, or ordered pair, is e comma 1. Able to figure that out without doing any crunching of numbers by hand, but you're welcome to do that too. It's actually pretty easy. All right. It looks like we have an x-intercept here at 0. You can verify that. I'm sorry, at 1. Of course it's at 0 in terms of y. All right. So what I need here, again, cross sections perpendicular to the x-axis is going to be a set of semicircles. So what I'll do is, because I kind of gave the best I had in drawing the diagrams on the previous page, so now you get the short versions. We know, and really this isn't going to be information that expires, the volume of one semicircular solid, aside from that 0 to 3, is this relation. So I'm going to steal this and use it again. All right, except it's not going from 0 to 3, it's going from 1 to e. And y isn't e to the negative x anymore, it's the square root of ln of x. So over the interval of 1 to e, pi over 8, the square root of ln of x, quantity squared dx. So that can go right into the calculator if we want. There's nothing wrong with that. Math 9, 1 to e, pi over 8. You put the pi over 8 outside or inside, it doesn't matter. In my y1 is where I have the square root of ln of x. So I'm going to put in alpha raised to y1, close it up and square it. And put the x, and we should be off to the races here. So about 0.393. Right? So we're just kind of using the information that we've already come up with. Never a bad idea. Just generalize. So for number 2, equilateral triangles, I'm going to go steal that work too. All right, so again, it's everything except for the bounds. Hit the wrong thing. That's a different worksheet. So I'll hold on to this. I need a diagram though. 1 minus x over 2. So 1 minus 0.5x, which is how I'll write that. And 1 plus, or negative 1 plus 0.5x. And x is equal to 0 is the y-axis. All right, so if we trim it so that we're only looking at the y-axis, something like this, I could bring it in a lot. Like how about negative 3 to 3? We probably don't even need to go out as far for x, maybe even just 2 units or 3 units. All right, so something like that. All right, so the base region is this triangular region right here, going from the line with the positive slope to the line with the negative slope. All right, so I'll just draw a quick sketch. Something like that. So this is the y equals, this is the one with the negative slope. So negative 1/2 x plus 1 is how I'll write it here. And y is equal to 1/2 x minus 1. All right. So if I want the base region to be appropriately represented, I'm going to need a rectangle that goes from the bottom one to the top one. All right. Now the perspective drawing is a little wonky there, so we just kind of live with it. But that's going to be the difference. I'll subscript these, so I'll call this y1, y2. The difference between y1 and y2. All right. Which is really what this is going to amount to in our quote-unquote formula. We also need the intersection, which is, it turns out it's at 2. Let me make that a little bit more perspective-y. So over the interval of 0 to 2, radical 3 over 4 times the y1 minus y2 squared dx, which in turn is radical 3 over 4 negative 1/2 x plus 1 minus 1/2 x minus 1
squared dx. Alright, so I can simplify a little bit. I'm going to run through with the negative sign, so I'll make a positive, negative, positive. We can combine some terms here, so I'm going to have a half, negative half minus another half is going to give me negative x. 1 plus 1 is 2. Whole thing squared, radical 3 over 4, and we're integrating over the interval of 0 to 2 dx. Alright, so now it's a matter of just popping this into the calculator. You'll see a different calculator here than what I was using mere moments ago, because this is a correction to a previous error that I made. So I just kind of spliced it in. So apologies for that. But it's still Math 9. It's just a slightly different look of a calculator, but it's the same general idea. This is the x84 calculator, the paid version. And it's made for touch screen devices. And it says 0 to 2. It's a TI-84 emulator. So I'm going to type in, because I simplified rather than using the y1 and y2 that I've stored into the calculator, I'm just going to type in negative x plus 2 squared. So negative x plus 2, close it up and square it, and then dx. It looks like I have what I need. Oh, I forgot my radical 3 over 4. My correction video almost had a mistake. Alright, so let me, where do I want to put that? I'll put that in the front. So there's the shortcuts. Oh, I put it in the wrong place. Same shortcuts, just in a different location. Takes a second sometimes for me. Alright, but that would be in the TI-84 if you were to do alpha y equals select n over d. That's what will come up. Alright, so this should be the correct response, 1.154. If you assume that that's some square rooted value, you can kind of sneak your way to a correct, exact answer, roughly, anyway. I say roughly because the 1.3333, that sometimes it shows up as 1.333334, and it's like, I know it's trying to say 1.3 repeated, but sometimes, because it's doing it numerically, it gets tripped up. All right, so this is the same as saying, because I squared this funky decimal to 1.154, we could say that this is approximately 1.154. Now this is a volume question, so we're talking cubic units. Now, because I assumed that this was the square root, that 1.154 was the square root of something, I could actually, by squaring it, get an idea of what it is the square root of, and that would be the square root of 4/3, which becomes 2 over radical 3, again, cubic units. Alright, so I just put the approximate one below because I guess that it would make sense that would logically follow from the exact value. So I'm just popping this in here, verify, 1.1547, blah, blah, blah. Oh, 1.55, apologies. Yeah, how did I miss that 7? Alright, and there you go. Just gonna center it a little bit, and that's it.
So looking at number 3, we have this natural log, we get this cosine function, and we have a solid that's, the cross sections are going to be perpendicular to the x-axis, but equilateral triangles. Alright, so I'm going to steal out information from the previous page. Alright, so let's get this information. Alright. So, same rule, but different scenario, obviously. I don't know if scenario is the right word, but you get the idea. So, different equations. So let me get the natural log in there, x squared plus 1, and the cosine function. Take a look, a lot of stuff going on here, but it looks like the bounded region is right here. So what I'll do is I'll just do a quick zoom box, just so I don't have to think. So if you select that one and then hit enter where you want the upper left-hand corner of your box to be, and then drag down and over to the right, and hit enter again when you've surrounded the desired interval, both in terms of x and y, and it'll zoom so that that is your entire window. All right. Looks like we're gonna need some stuff here. All right. So, but first off, I'm just gonna do a quick rough sketch. Poor quality, of course. Alright, so we're looking at something parabolic. I'm going to smidge that over a little bit. Perspective wise, I don't know. It looks like it might be a little off, but I'm just seeing what I can do here. And then something like this. I think it's got to be more like this. Not perfect, but I think it'll do. Alright, so I'm going to need those intersections. Now, obviously my diagram doesn't tell the whole story, but it does look on the calculator as though it's symmetrical. So looks like 0.916 approximately. Oof. Oof. Ah. I don't know if I like that, but I'm going to live with it, I think, because just looking at the functions themselves, I mean, we got the natural log 1, so I'll jot it down here. I'll call this y1, just so we can distinguish one from the other somewhat easier. ln of x squared plus 1, and then y2 cosine of x. The intersection would be when they're equal to each other. Right? I mean, to solve that equation doesn't seem like fun. Or maybe it is fun, depending on your perspective on things. I mean, we can give it a quick go. You know, this would be log base e of all of this stuff is equal to cosine of x. E to the cosine of x is going to be equal to x squared plus 1. Then it becomes a question of, all right, well, how on earth do I solve this? You know, normally when you want to get an exponent, a variable out of an exponent, you take the log of both sides, and that's just going to bring us right back to where we started. So this is a use the calculator situation. All right. So 0.916 approximately, and 0.609. All right, now let me just show you something real quick. If I hit X on the home screen, it has stored in the value of the intersection, and it did the same thing for Y. So if I did alpha 1, well, actually, I mean, you could use the xe theta n, or you could hit alpha store, it'll do the same thing. But we have more exact values here if we want to work with those, and I think we do. So what we're going to do here is write the approximate values, but use the more exact values in the calculator. Alright, so this is going to go from approximately negative 0.916 to approximately positive 0.916. The y, that goes back to the arbitrary rectangle business that we've been doing all along. That's going to be the difference between y2 and y1. Right. So the thickness being dx. Now, since I denoted y2 and y1, you know, it's a sort of a de facto key. You know, it's not exactly a key, but you know, it's close enough. I could actually use the notation y2 and y1 here. Because I've stated in the solution to the problem what y2 and y1 are. And shockingly, I kept it in the same order that I had it in the graphing calculator, which is good news. All right, so what I'm going to do here, well, sometimes the calculator can be a little nitpicky about notation, and then sometimes it's absolutely right. You know, like it's right to be nitpicky. In this case, it'd be one of those situations where it would be right. If I do math 9 and I put in the radical 3 over 4, I'm actually going to put the radical 3 over 4 in front, just so it doesn't get too congested. If I put a negative x to x here and then tell the calculator that the variable I'm using is x, the calculator is going to have a fit, right? Because I'm telling it in the same breath that I'm working with something that is both a constant and a variable. So the calculator is going to be like, well, Well, no, you're not. So it's going to give you an error, or it'll just flat out give you the wrong answer. So you can do this one of two ways. One, I could just type in the values. So that's manageable. And then alpha trace y2 minus alpha trace y1. Close it up and square it. So that's one way to go. And I might as well just jot this down because it should be pretty spot on to the correct answer. So approximately 0.3967 cubic units. All right. Another way of handling it, if I have x, we know x is going to be that 0.91 blah blah blah, the more accurate one. I can store that in as something else. I'll call it A. So every time I hit A, it'll bring up that decimal. All right. The benefit of doing it this way is if I use the intersect function, it's going to give me a different x value. Might be completely unrelated to what we just came up with. And so I now have a way of hanging on to a previous answer for the long run. All right. And so what I would then do is in my integral, I would just type in negative a and a positive a, and let it spit out the answer that way. Turns out it rounds to the same thing. It's actually off the grid, but I'm pretty sure, I mean, it's not exactly the same, but it's close enough that we're not going to doubt it. All right. So that's a pretty solid way to go. And the other way is another way that I've been talking about all along, and that's Desmos. All right. So you put in your original functions, and you can use subscripts if you want when it comes to Desmos also. All right. So when I go into Desmos, I could say something like y1 equals this was the natural log of x squared plus 1. Desmos understands the subscripts just fine. All right, and y2. All right, now how am I getting the subscripts? Because there are fun ways of selecting subscripts on the calculator on Desmos, but it's just type in the variable and then type a number next to it. Right? It actually is set up so that you don't actually have to go and look for special keys in order to get you to the give you the ability to use the subscript. Right? So the cosine of x. So now we have our two graphs, very nice looking. Right? That's always a benefit of Desmos. Click on it, and you have your intersections. All right, so you can go that route, and then you can, just pretty much do what we did here. Let me just bring it all in. Function. We do negative 0.916, positive 0.916, radical 3/4. Then we had the y1, what was it, y1? It was y2 minus y1. Close it up and square it. I forgot to open parentheses for the whole thing, so let me do that. Alright, and so you get something, that's completely wrong, which is always a good thing. Yeah, that was kind of strange. I don't know why that. that power turned into just an ordinary tube, but it did, and we learned from it. So fortunately, we had done it other ways before, so the expectation of what the correct answer was in front of us. So, so there you go. All right, so you can get it that way.